you envelop it, then you make your finger extremely stiff, and therefore you can apply force on it. So it gives you a safe mode, and then it gives you a force application. So that allows you to do interesting things. Just look at another silica particles. And we basically particles with lasers, and then that enables us to make sure that we can give you assurance that we haven't changed your cell characteristic.
Robots can be very useful in applications that might be too dangerous for humans. At the USC Viterbi Center for Advanced Manufacturing, we've developed Atoms, a robot to do machine tending tasks. We are modifying this robot to perform disinfection tasks in public spaces, such as offices, labs, schools, hotels, and dorms. We're calling this Atoms UD. Atoms UD.
Okay, so soon after basically pandemic happened, so there were two major modalities of disinfection. One was basically use UVC lasers, right? And people had this platform with a huge column, right? Where you can drive this thing around and disinfect. So the trouble was that you couldn't do disinfection of things which are not directly visible. So here the idea was use a mobile manipulating platform where a person sitting at home can give some high-level commands to the mobile manipulator. And of course you will have a UVC column. It's not like that you go shine a little later. So you're going to disinfect majority of the UVC column, but things that matter to you, you can just go there and basically hold it laser on and disinfect it. That enabled us to build a system basically, because we've been building this for machine tending anyway for a while. So we repurposed it, we did some interesting experiments with that. And that was an interesting project, but we were able to do this. Just has all this ability of picking things up, opening things, and a remotely located human supervisor that can either completely teleoperate or interact with it at a pretty high level interface. So both options. And we build regular stamps and all this stuff. Okay. The second platform, now unfortunately what landed up happening is that people were still not comfortable with laser-based labs because there was no way for all of the strong patterns you could basically with the spray base.
We decided to build a disinfection system using a highly agile electron. Our robot is called Laser T.
So in this case, we are basically using a legged platform. It's exactly the same idea. Remote control operator operating this thing from tablet, but in this case we're doing chemical spray. A chemical spray, the guidelines are that if you can spray it and you can, as long as you can build a minimum thickness, you're completely safe. And fluid basically flows, and therefore once it's done, you can just image it and give guarantee that I've done this. With the laser stuff, giving guarantee becomes very, very hard. Like a platform enables it to go basically to places where a real platform can go. And in this case, we were using basically body manipulation capabilities to do spray and not did. Again, in this case, the idea is let human not worry about doing course challenge, but sit there, give high-level command when necessary, completely take over the control and do roll out.
So how real time is the human interaction? It's like human plans, we try for entire room and then the robot does the room, or
humans usually just giving it waypoint and a target surface, and the robot is just human is monitored. But in this case, it's completely monitored by human. And human feels that, okay, you've not done it again, the right way. And in this case, we have deep learning based image which can then capture it and show you what the robot thinks that you have.
so all this navigation about the robot.
All the navigation from waypoint is all. Now, human may decide that's not what they want. They may take over. So this have full, sliding board control, right? All the so that's kind of what happens in that case. Now, in this case, typically what happens is that this is a composite layer problem. So a lot of aerospace companies nowadays make it part of aerospace composites. So some process composite manufacturing is a fully automated, but it is one process which is called sheet layer, which is a totally manual process. Usually, two humans will be laying a sheet. One will hold the sheet, another one will do the layer. Now, this is, as you can see, is a tedious process. Now, idea is that why not robot hold the sheet? And human only do the challenging part of it, and robot can hold the simple part, because remember, you have to apply pressure to make sure that this thing actually is compacted. So then, why not do it immediately? Right? So that's what we were exploring in that. And you can then eliminate two human 100% duty cycles to one human 50% duty cycle. So you can reduce the human burden basically quite a bit. So here is an example application actually where human is doing high value assembly. Where they just sit at the desk and they can just command the robot to bring them parts and whatever they need, robot will go basically fetch it. So that way human doesn't have to do this routine, right? And robot will do a system. Tell the robot, get me this tool, robot will fetch it. Tell the robot, get me that part, robot will do it. And the human is just following some high level work instruction. And in this case, we're using some AI technology to see what human
Do you want the suggested part?
what human may or may not want to do.
I want the suggested part.
So system is kind of learning as human is doing things, what they may do. Then they say, should I bring you that part? They can do some prep work automatically, so that's kind of what things are happening here. And this is what is being done a while. And this, in this case now, the platform is completely autonomous. That human have no ability to control it. All human can do is that, get me this part, get me that tool. That's the level of interaction. In this case, you see that we are using speech as a modality for interaction. There are two robots, one is which is for fetching, one robot is mounted on the table to basically push the part to the appropriate. Now, we are not directly handling basically parts yet because we are using auto markers, that's what part is bin, but this technology currently we are working on it is directly using all the tools using machine vision and not having to rely on this. So that's what's going on here, where we really want to eliminate the need for human to do routine, mundane jobs. Right now, in many of these kind of settings, human perform a lot of these things. Okay, prep work, go there, get the tool, get the part, set it up, then do it. You want human to do high value added part, not necessarily routine. So this gives another perspective on assembly. So in this case, we are doing complex satellite assembly. We're building a satellite by robot, 5 different robots are building it. Now, there are certain tasks which robot cannot do. The current generation robot cannot do. So your perception ability is not there. The robot will do it. Those tasks will get assigned to you. Now, what ends up happening is that sometimes your uncertainty is so high that robot will not be able to do it, right? So in that case, robot initiates. So this is introspection AI, which is embedded in these robots. They analyze it, say, okay, force is building, I'll be unsafe, and therefore I'll call human. So all the human help stuff basically initiated by robot, and then human help is solved. So if the part don't get loaded the right way, if somebody accidentally puts the wrong part, robot will detect and then let them know, I don't have the right part. So all the validation stuff are being integrated basically in the cell. So then it will again initiate that so that we get the right part and you can swap out the part. And in this case, we are running a digital twin in parallel. So somewhere a person can watch on the camera feed the digital twin as to what ought to happen. And if they decide that we can do it. So yeah, so this is showing different failure modes.
So the digital is sort of predicting what the robot should do.
So it's in one step in advance, it's showing
Yes,
you
yes.
what based upon the current state.
Yes.
So it's not a simulation, it's a digital twin. It's watching, it has gotten all the current sensor data and then it's based upon saying what my program is, what am I going to call. Here. And in this one, we are controlling the robot by gesture. So we have a gesture. Yeah, and if you put the part in an unreachable thing, you look at it, analyze it, says the part is not reachable. That stuff can happen, and we also do human tracking. So if a human enter a non-collaborative zone, next to industrial robot, cell shuts down. So, yeah, I mean, just kind of different modality of bringing in human, tracking them, gesture interface, speech interface, these are different things we are exploring. Now, this is our most recent. Where the goal is to go away from putting the parts in the bin. Directly, basically train glasswing so that you can pick up the tool, identify and pick up the tool. So in this case, we are able to pick up tool directly. So in this case, using basically point cloud to identify the tools, figure it out the glass planning, and then go ahead and pick them up. The goal here is to eliminate the need for all the Maruko marker based practices. So that's what some of the more recent work is. Now, last part is entertainment. These are my first year undergraduate students who have been playing with their first playing the robot. You get them backstairs, they do something interesting with it. So these are first year undergraduates. So they decided to make pancakes. They always do something entertaining fun. Their goal was to draw a pancake shape on the screen, and then robot can then we analyze it, and then we will basically get robot to use these shapes. So, give it one. This is the two-color pancake thing that they have built. And Baxter robot accuracy is pretty bad. So it is accurate. It's not a very accurate. It creates a mess. But the pancakes still are delicious. Another interesting way of getting students excited about what. Okay. All right. So now, traditionally, the role of robots have been to reduce the cost. So people said, okay, let's reduce the cost by deploying robots so that people don't have to do dull, dangerous, dirty things, and therefore the company which is deploying robot hopefully makes money and they are happy, right? But you're not looking at it from the perspective of your workers, and you're not looking at from the perspective of your customers, right? Management is looking largely from their perspective, right? How can I reduce the cost and therefore make money? Now, modern perspective is that, hey, why not use robot to enable innovation? You can do things differently so that our customer perhaps can go more value, right? So people ask me, what's an example of it? So minimally invasive surgery is an example, right? So use of robot enables new surgical procedure, right? Which is good for the patient. So obviously, it's a good business case, right? But it is largely focused on enabling innovation. That's the main driver for it. Then increase productivity. So enable your workers to make more money. So they're more productive, they're doing more high value job, hopefully they're being paid more. Right? So your workers are happy as a result of embracing it. So the good example of that would be the surface tension, right? So let's say a body needs to be sanded. 80% of this is a very boring, mundane routine work. Maybe 20% of this is intricate work where these skills are needed. Then why not just let the robot do 80% of it and let the human do 20% of it? And then you can employ a more skilled person because they can man be working free of themselves, and hopefully their life is much better than this one. And they're programming robot, supervising robot, so hopefully they get. So that's the productivity angle. Third angle is the one which I told you before. So robots, basically fundamentally alter the nature of work. Since they're altering the nature of work, why not exploit it to create employment opportunity for people with disabilities and help them get work ideas? This is a new perspective, right? Rather than saying, okay, management is going to make money, right, by using robot, what you're saying, as a worker, why should I, basically be excited about it, right? As a customer, why should I be excited about robot? And as a society, why should I be excited about robotics? Because it basically enables more opportunity for working. Right? So that's a different perspective. So our work is focused on this other perspective, right? Okay. We're looking at from worker perspective, we're looking at from society perspective, we're looking at it from customers, right? And saying what can we do for it? So let's see. We are at about 110. So I'll now introduce 3 problems and basically just introduce the challenges, and then you can read up the paper together. Alright. So first problem. Yeah, in the interest of time, let me just go through this very quickly. So robots are popular in manufacturing. They increase throughput, improve quality, prevent injuries to human. That's it. All modern perspective points, right? Robots in agriculture, from societal perspective, they greatly introduce waste. So in agriculture, when humans do things, they waste our water, they waste our fertilizer, they waste our pesticides, right? So robot actually eliminate all the waste. So society should be excited about using robots because we are using our natural resources in a significantly better way. That's the perspective of using robots. I'm trying to give you an example of modern perspective, right? Robot in construction, basically, again, the trouble is that, as you know, if humans are going to work in a construction project, right? Nighttime, you cannot operate it, you risk, and you get hurt. You want construction to happen very, very fast so that you can get back to, not disrupting our life and enjoy the benefit of it. Right? So again, robot can speed it up and dramatically reduce the injuries to humans, right? So again, both from worker perspective, society perspective, robot, great things. And robots in warehouse logistics. So once you start removing humans from the warehouses, you can make the warehouse vertical, which basically significantly reduces the land area needed. And also, in principle, you can basically run a warehouse at a significantly wider temperature range, which then basically makes them environmentally much more friendly than have a massive warehouse range, and therefore you're really bad for them. So lots of other benefits of using robots. So all I'm encouraging you to think about is that don't think about robotics purely from the perspective of cost. That okay, it's going to replace a human, great, and we're going to make more money. Right? That's not how you should think about it. Right? You should think about robotics saying that would society benefit from it, right? What environmental benefits would be there, inclusivity benefit might be there, worker health benefit might be there, and then from worker perspective. I mean, would worker be better off, right, in terms of their health, in terms of their productivity, in terms of upskilling? Because who wants to spend the rest of their time in life standing, right? If I become a robot operator, I can make lots of money. Perhaps after a robot operator, I can become a robot maintenance person. I can make even more money, right? So all of us want career progression, right? So robot could enable it, right? And then finally from customer perspective, right? I mean, what value customers get? Not that okay, it's lower my cost by 2 cents. I mean, are you going to offer me better, inherently better products, right? So that's the. So if you want to take one message from my class, today's presentation is that, right? You should always be now looking at robotics from the perspective of customer, perspective of the worker, and perspective of society, and ignore the management perspective, right? Okay. So that's what I would encourage you to think about. Okay. So in the remainder of the time, let me try to now run through the technical slides as fast as I can. Okay, so the first project I'm going to talk about is basically when you deploy these large robots supervising human teams in search, rescue, recovery type of operations, time is super critical. You make one bad decision, even if it takes 5 minutes to recover from it, somebody might die. Okay? So you cannot afford for human supervisor making good decisions. So this is the project that we will be working with, basically Army Research Lab for a while. So multi-robot teams, people are thinking about deploying in a wide variety of settings. Humans are going to be, so all the scenarios are robots are being sent out, humans are sitting in a room, control centers. Once in a while, they're getting update from the robots, and then they can issue whatever level of command that they on the remote, completely remote control it, retask it, whatever new information comes in, they can now, in challenging situation, and now question is why do you need human supervision? Because many of these scenarios you are basically dealing with human lives and injuries to humans, right? And therefore, robot not going to make those decisions. The robot is not going to make a decision that I'm going to save him, but not save him, right? I mean, no way any society is going to ever agree, right? So human supervision is critical part, right? Where human can bring in all this, thinking that what the priority should be, how good we are, and so on, right? So human supervision. So what happens when humans get involved? With massive uncertainty, right? Confusion for humans. They are very stressful, cognitive overload, a lot of things are coming at them. And emotionally you are fatigued because you're seeing people hurt, all sorts of things are happening, right? So what happens in these scenarios? That we know people make errors, right? So when all those things happen, people start making errors, right? And when the errors do get made, then bad things happen, right? So what do we know about preventing errors, right? And how can we make sure that humans don't make errors? So one technology that we have known for a long time that can prevent human errors are alerts, right? Cognitive alerts. And so nowadays in cars you have that, right? I mean, if you don't, brake hard enough, it gives you warning. If some obstacle appears, it gives you warning. So you get all these alerts and warnings, right? Which hopefully prevents that kind of mistakes. The alert is a useful concept to prevent human errors, right? have been exploring this, right, in a very complex scenarios, what you can do, what kind of things causes problems. However, the kind of pure sensory generated alerts are not going to be useful in this multi-robot setting. Right? The trouble is that, okay, you have the priority, you had set the new robot to go there, you search there, and if you find something, come back to me, and then if you see a robot that has been stuck, then report to me. So you've done some complex tasks. Now, something were to happen, it will have all kind of effect, oscillating effect. And sometimes you cannot just see what's going to happen. And that's where the alert technology becomes really useful. So we need new type of alert technology. So we have been studying these complex missions where you have a large area, a team of robots searching it, there are all sorts of events that can happen there. Humans are tasking at a high level, not remotely driving the robot, but tasking at a high level. But the robot talk to control station only once in a while. The relay robot will bring in the large environment, so therefore continuous communication are possible. So you get different kind of updates, that found some object of interest, or the robot, other robot has been disabled, a rendezvous won't happen, and so on. So these are all complex things. When the information comes from the robot, human will have to make decisions, right? So we studied it, how good a job humans basically do. We did human subject study. It turns out that in any complex setting, you start now exploring this, what's going on. So this study was done by 10 humans. Now we finished another study, 20 humans. The paper hopefully will be submitted soon. I mean, 10 people could not make any good decisions, right? Meaning that they were good decisions, meaning that the way they were contemplating retasking, that would have caused problems. Right? Significant delays in right action. Now, on the other hand, if you start issuing alerts, then basically people can make really good decisions. You warn them. Okay. Consequence of this is going to be. Now, the trouble in this case is that there's a lot of uncertainty, right? Because this robot reported to you at 10:32. Now, this robot might be somewhere over there by the time you are about to. There's all kind of uncertainty. Everything involved in the scenario, humans are not very good. So how are we going to generate the alerts? And this is time critical, right? We're going to do it in a very short period. So the technology that we use in this case is basically forward simulation, right? We're going to do forward simulation with all the uncertainty and assess different event probabilities, see what might have happened, and therefore we can tell you that 90% probability this may happen. You may want to rethink your strategy. It's all probabilistic alert, right? So we use MTL to define those alert conditions for super high-speed forward simulations. Now, obviously, if you use your naive way of doing simulations, then you cannot compute in real time. So you have to do all kind of advances in the simulation. So we have been now using discrete velocity event-based simulation, which speeds up things dramatically, where you basically are not going to do continuous robot motion simulation, you will do a mixture of certain discrete velocity things, that's how we model the phenomena and get the right level of probability in the simulations. So we have shown that these discrete velocity type of things can, even though it's doing approximation, but your error estimates are going to be better than what you're going to get by doing this. This is just showing you alerts. You can read all our papers in this area. And in this case, basically, we did show that we can use in real time, issue useful alerts. Second problem that I want to briefly touch upon is human-guided manipulation. So this is a fundamental core technology, whether you use it for disinfection or you use it for machine tending or explosive disposal problem, which is the fundamental problem of human-guided mobile. So this example is basically disinfection motivated example. In this case, robot arm mounted on a base. Adams 2.0 is the platform used for this one. Again, totally sliding autonomy on this. Okay, I'm going to skip some of these. So alert in this case are again where robot is driving around building uncertainty model. And in this case, what we do is that you try to image things from many different angles. And you fuse the data. When you fuse the data, in the fused data, you try to estimate what uncertainty is. Then based upon that level of uncertainty, you compute your plans and say, okay, under this level of uncertainty, what is the probability they can negotiate around it without colliding? If I can, then I don't need to alert you. I'm happy to go do it, right? But either my camera is not functioning well, or space is so tight that I cannot safely negotiate. In that case, I can compute and tell the human, look, in this case, if I perform this operation of inserting this part in this machine or doing something, right, or taking it off, I might collide, right? Then human can intervene and help them, right? Again, all of this has to happen in real time. So this is basically the alert solution model. It generates alerts and helps the human. Here is where the problems are. So you can model alert conditions again in this case, by decomposing your manipulation operations. Compute your uncertainty. Then by using some ML techniques, you can certainly recompute, make things super fast. And then you can build these right kind of map and then give it to humans. So that's the idea, that where you can say, in this case, uncertainty is telling me that no path that it could exist will not have problem. And human can visualize the plan, they can see, okay, which side camera is not imaging the other, and therefore they can insert another waypoint and say, go via this way. That's the work. Third piece of the work that I would like to highlight would be managing robot workload. So a lot of people are now talking about robot as an assistant. Robot will be fetching me. Now, you know that in today's on work warehouses, that's what happens. Robots are bringing in all the parts to the similar setting in the manufacturing setting where robots will bring you all the parts and tools. The trouble is that in that case, if you overload a robot and demand too much work from them, then robot will start missing deadlines. So you would say, bring me this tool by 2:35 and bring me this part by 2:36 and bring me this by that, right? If you overload, now of course the deterministic problem is very simple. You answer it in a binary way. Yeah, you're overloading, right? But the moment there is uncertainty, everything becomes problems. So I can say this deadline I'll miss by this probability, this deadline I'll miss by this probability. So this is now negotiation between human and robot, right? So robot is telling you that, okay, the task that you have assigned me, I'm just going to get towards the end. So robot can then tell you that, okay, the task that you assigned to me, the way you have done the assignment, here are the couple of things that you can try. You eliminate this task from my list. Everything else I can finish it with 99% problem. Alternatively, for this task, you relax the deadline. Don't demand it by 4:32. Give me until 4:40. And then I'll do everything by 99%. Okay? A probability even is specific. Nothing magical at all. Okay? Human can come back and negotiate with the robot. Tell you what, that task you got to do it. Tell me something else, right? So in this case, robot is solving this constraint solver, right? Where initially you have to keep it like that. But you can suggest something. So with this negotiation, then human and robot very quickly can come to an agreement whereby robot task loading is right balanced. So that it's like working with an assistant. If you have an assistant and you overload your assistant, then your assistant is not going to be able to do it, right? So this is a framework for negotiation between robot and human, but using all your mixed integer programming formulations. And we are solving this optimization problem. doing sensitivity analysis in terms of our deadlines and which tasks get assigned, and therefore we can give some meaningful suggestions, right? And of course, the computation of this problem is hard because you cannot just have a single plan. You have to look at family of plans, hopefully diverse family of plans, and each family then you can figure it out what is necessary. And again, computing this all in a reasonable fast time is the challenge. Okay? So with that, again, you can read this paper. So this is a mathematical framework for human-robot negotiation. People have studied this problem before, but all of that is not based upon a mathematical. It's a very ad hoc framework, right? But this is doing mathematical analysis and sensitivity analysis, and then bringing in more mathematical framework to this human-robot negotiation. Okay, so future directions. So one of the biggest problems that currently as a robotic system faces is robot can be super smart, right? But robotics technology is not trustworthy. People don't trust it. So, we have to really make sure that in future we not only design robots which are smart, capable, but also we need to design robots that can be trustworthy. Right? Trust has 4 dimensions to it. Unambiguous communication. The robot tells me something I should not be confused about. Right? Or when I tell robot something, its interpretation of what I'm telling it, it cannot be confused about. Right? But that immediately starts raising questions. Then ability to explain the thing. So a lot of AI that we have been all pushing in the robotics, black box AI, robot cannot explain anything. It just tells you my deeper importance, right? Not much better. Right? We really need to make sure we start exploring explainable AI in this framework. And consistency. So a lot of again technologies that we are very fond of using in robotics are sampling based and random sampling based method, which will in the end generate one time path like this, another second time path completely different to begin, complexes to consistency becomes a major problem. So we got to explore that and predictability, so that we should be able to predict robot action, robot should reliably predict human action, so all that stuff needed for us to realize these technologies. Now, as we deploy more and more learning technology, building trust becomes harder. That means even harder and harder. So we really need to now, again, start thinking about how are we going to engineer about entire machine learning to make sure that we can build trust. And some of the recent advances in the field are basically physics-informed AI. So where we will make sure that AI at least will leverage as much physics as possible, right? Whatever is reasonable, we will exploit it, and also concept from safe learning we have to also bring into it, so that when robot is trying to do things, it will remain safe and therefore hopefully engender trust. Now, trust building is a process, right? So you have to treat this like a process, right? You don't trust something immediately. So you follow the process, you try it out in a baby step way, and then you start trusting. So we have to roll out some of these technologies the same way. So robotics as a community has made tremendous advances in terms of making technology smart or intelligent. And we see lots of them. I'm not saying that that will be solved, right? But I'm saying a lot of focus has been on it, right? But focus on trust building has not been there. That's something that we have to collectively start exploring. And how can we build trustworthy systems? And then, of course, we need lots of innovation in interfaces, because humans are going to be a part of it. Obviously, we have augmented reality, haptics, some speech, but are these only modalities through which people should interact with robot, or are they something totally out of the box new modality which we have not thought of? Right? So that's a research question that should all collectively answer, because right now we see a lot of focus on speech, we see a lot of focus on augmented reality, a lot of focus on haptics, and those are all fine technologies that we definitely be needed. But we are not seeing true innovation in terms of totally out of box, interface technology. I mean, again, I'm not saying that speech or haptics or augmented reality will not play a role. They will definitely play an important role. Perhaps we should think about other modalities as well. So that's a summary of different challenges. Okay, so in conclusion, advent of human-safe robots have enabled all kinds of new ways, new applications, new ways of thinking about it. Physics-informed AI is useful, and I show you several different examples of it, where we needed to compute things super fast, minimize the data needed to train systems, so that gradient of many of our successes and success of many other laboratories. So we have to keep exploring, keep advancing. So yeah, so with that I would like to conclude and thank all my students who contributed to this presentation, all my sponsors, any questions.
Those who have questions, please raise your hand.
10 minutes, right? 10 minutes.
Yeah, 10 minutes.
Okay.
So I have a question related to the So I have a question regarding the last slide that we had, which talks about planning robotic tasks and having some form of utility. So let us imagine scenarios where so let's say that, for example, sheet assembly. You can equally have a robot or a human do certain tasks. Now let us factor in everything. Let's assume a complete information that you know the power consumption, you know the economic cost of everything. Now there are these standard economic models which talk about utility maximization and incentive design and all of these things. So have you also been looking at these economic frameworks where your task is to design an optimal schedule, but you have to keep contract remunerations into account. You have to take into account how to maximize productivity and all of these things.
So, answer, I have not. What we end up doing is that we a priori, kind of divide up tasks, the task which should be done by humans, the task which should be done by robot, right? So this is done in consultation with some industry engineer for a facility. They decide humans will do this, robot will do that. Humans only then come in to do extra tasks and continue to do it. But not to say that one cannot design it. And I'm hoping those industry engineers will do this task as they are recommending that this task is done by humans.
Anyone else?
I mean, so the question is, I mean, in all this work, right? I mean, for example, disaster scenarios, right? It seems that there is a certain assumption of what is known, right? I mean, disaster scenarios, unlike we have a lot of data. I mean, data collection during disaster is probably not a thing even now, right? And then the question is, I mean, what are you assuming so that the remaining uncertainty is manageable, right? I mean,
Yeah, so in this case, the assumption is that you know the map. I mean, you have basically a map. Now, again, map may require significant update, but as the robots are going there, you may find a passage to a block. You're assuming that you're given an initial.
okay. Somebody has given you the current state of the disaster.
Initial map of how things look there before disaster.
Okay, before disaster.
Before disaster. And then you're saying, okay, I'm going to try. So there's supposed to be a building here. It's supposed to be a bridge here. It's supposed to be a road here.
Yeah.
So I will try to leverage those. Right now, obviously, if once I go there, it's not there. That's what I was saying. That's where the human robots start reporting things back and saying that bridge doesn't exist, right? What should I do now, right? So now you see, okay, you were thinking that I can use this bridge, go there, rendezvous with other robot will delay it back to me. So immediately now you know that that's not going to be possible. So that way you're generating an alert. You're saying that which future tasks now based upon what information available, became just as now available, is not feasible in the future. And if you're not paying attention because you are worried about some other aspect of it, right, then alert system will tell you that you might be focused only on this implication and this implication, but there are 4 other implications. So that's what alerts help you.
So for alerts, do you have what kind of guarantees do you have? Like, do you have results like what it says that you have alerts, you have efficiency improvement? Is it analytical or is it just some case studies?
Alerts in this case are basically you have specified a spatio-temporal event. All of them are basically robot will be at this position at that time. Everything is broken down to that line, right? Okay. And you are big, so of course, if it is time, then you get some spatial resolution. Or if it is spatial, fixed, it will become temporal constraint. And then you're basically saying what is the probability that event will happen, right?
That's why so I'm asking like let's say whether there are alerts, right? So what you're saying is alerts, your human have better capabilities, right? But is that guaranteed? Like, what kind of
So that's why we do human subject study, right?
right?
All we can say is that alerts are computed correctly. That's it, right?
So I mean, how do we know that those are the correct kind of alerts we're looking for?
So in this case, human define what alert they need, right? So remember, they're managing the task, right? So they are saying that, okay, I would need 4 robots in that region, right? At that time. Now, if some bridge is broken or something has happened, right? Alert system will tell you that, look, your desire to have 4 robots in that region by 4 p.m. is not going to happen, right?
So the alerts are entirely fixed. What kind of alerts you were trying to look at?
Yeah, human can introduce MPL conditions. So human can throw in any new MPL condition whenever they want. System immediately will compute and tell you, okay, whatever condition you give. Now, of course, we are building an interface so that we don't force a person to write MPL code, right? But at a high enough level, that's what happens, right? So you make a requirement that I want this robot to be there at that time, and this is the probability threshold, right? Whatever people are telling you in English, you are translating that into a condition, and that is then driving those, basically from that simulation, extracting an issue. That's what.
Forgive if I count down, but as a student, what can I do, or from where I can approach to support this course?
Which course?
No, the robotics field and all, from your industry experience.
Okay, let's do the following. It's a very good question, and I will answer it, right? But let's see if there's any technical questions first, right? Because if I get into that, then I might go for a while. I may not answer it, right?
So they were talking like to build trustworthiness, there can be a connection between users and like the machine. So it can be like maybe like self-driving cars. So shouldn't all of the right now most of it depends upon the ones who generate or develop. So can the user also contribute in some sense? Maybe in self-driving car they can choose predeterminedly how to like there are some scenarios in self-driving where it's still not solved that that's philosophical. So
Right.
can user do personalization that maybe that when it happens that they click a button legitimately, but there should be maybe some options are given by the one who develop, but the user chooses which to happen at what time. So are there any examples?
Absolutely. So users are an integral part of any trust building process, right? So user will play a role, whatever process is being followed to build the trust, right? So if user believe that, okay, explainability is important to me, right? Then user will demand that, right? The user would say, if you give me more options, right? That's how I'm gonna trust the system more, then that has to be explored.
So,
Right?
so are there any examples going on right now? Maybe any example you remember right from your experience?
So I mean, a lot of people who want to build trustworthy systems are working with user groups, right, to figure it out how this technology will be deployed. The point that I was trying to make is that in traditional robotics, there's a lot of effort which goes on building trust, right? Okay. It's once you start deploying machine learning, that's where community is not doing a good enough job, right? A lot of machine learning is black box mode, right? Okay. So traditional, so when factory people deploy a robot, right, using classical planning, right? I mean, they work with the users to make sure that they fully trust it, right? Okay. But they are not using any advanced machine learning, right? But I'm saying as people are rolling out in advanced machine learning technology, right, the burden is on us as a community to make sure we start thinking about trust, right? Because if we roll out completely black box machine learning and some unpredictable things will happen, people are not going to trust it.
So like in real time, so
Right.
it should be developed by the company only. Like the options will be given user, but it can't be
Right.
user can choose anything on its own. So maybe like there's some scenarios in self-driving where someone will predict something else, someone
Right.
So
Sure,
like maybe for that in real time, that will be in the starting, but like when it happens very rarely, so they can have an
Right.
option. Like in real
So
time.
absolutely. Yeah, the user will have to play a role in it, right?
So are there any happening in real time right
I do not know about what's happening in self-driving, right?
No, maybe like in common, not only in that domain, like in robotics.
I mean, so that's what I just said, right? I'm saying people know how to do this really well in the absence of machine learning, right? In absence of machine learning, people have mastered this, right? Because no industrial robot can be deployed unless you have gone through the complete use case and saying, okay, you see this person should be doing this, right? However rare that event might be, right? If this person should be doing this, right? So they have modeled it completely, right? It's just that when you start deploying machine learning and the world becomes a lot more unstructured, that's when the people have not studied it. That's what I was trying to say, right?
Thank you.
So, can you comment about the gap between the capabilities of these classical planning, act, control kind of robotics versus what is claimed by these black box machine advanced ML-based robotics things? I mean, I'm familiar with autonomous driving, but I'm just trying to understand also in other applications.
Absolutely. So basically, when the world is completely structured, where no uncertainty exists in manufacturing, and you don't have very high level of clutter, moderate clutter, completely structured world, classical techniques, classical AI techniques, which are basically heuristic based planning, your mixed integer formulations, branch and bound search, seem to work reasonably. The trouble starts when words start becoming less and less structured. So you have dynamic obstacles, you may have challenge in classifying the obstacle, you may have large amount of uncertainty, partial observability. That's where the trouble starts moving, right? Now, the classical techniques, you don't have good heuristics for any of those problems. If you do brute force it, it's just going to take forever. So that's where now people are bringing in this modern machine learning, right? That I can do some deep reinforcement learning and pre-train the system. Now the trouble basically start happening is that in that case now, what is the consequence, right? You don't fully understand it, that okay, if I misclassify an obstacle, and based upon that I was going to use some machine learning framework to take the next action, what would happen? Right? How bad things can get, right? So that's what we don't understand. Right? Now, obviously, those systems outperform the classical system, right? In many of those things. But trouble is still is that there will be some edge cases which will sneak in where people just do not know what is going to happen. So that's the problem.
So, just a follow-up question. I mean, in your opinion, where is this going? Which direction is it going in? I mean, one thing that I've seen is people are trying to sort of bridge this black box versus white box classical technique. I mean, having end-to-end pipelines which are neural network based, but then sort of within that pipeline there is more structure in terms of, you know, for example, Raquel Astosun, who's now running Wabi, which is another, I mean, she was heading Uber or autonomous driving at some point. So they have papers in CVPR and all where this kind of a structure is being imposed in an end-to-end black box system. So
so similar things. So that's what the physics informed AI is all about, right? At least the domain where I'm playing, right? So idea there is that, okay, so it's a gray box approach, right? So idea is that, look, so let's just take a more complicated. So let's say you're trying to do, you know, very accurate prediction of what where the robot will be as a result of modeling, right? Now, your classical kinematics model, rigid body kinematics model, can do millimeter scale prediction pretty accurately. Now, the trouble is that you cannot do, you know, beyond that because say leg may bend, backlash, and so on and so forth. So rather than using a pure black box neural network, which will be data hungry and you don't know what crazy prediction it might do, the better approach might be that, hey, I'm going to use classical, I'm giving you a very naive approach, right? I'll use classical DH parameters and get my 2 millimeter scale prediction. Then I'll train a neural network, which will do further corrections, right? But I will make sure that any correction that I do are only 2 millimeter scale. Anytime I'm going to see anything beyond 2 millimeter, I'm going to kick it out, right? So now I can give you guarantee that suddenly my prediction is not going to be off by a centimeter, which is going to crash into it. Now, then I can design a system where I can say that, look, 2 millimeter I'm accurate by DSR. 2 millimeter correction I'm going to do. Now, if my collision margins are beyond 2 millimeter, rethink, right? Okay. So I can implement a system like that, right? So that's where people are saying that can you combine the physics, push the boundary. When you have the last 5% correction that you're doing, then start building in safeguards. And if things are not looking good, take a pause, get humans, or do some introspection. That's kind of what the thinking is. So what can you do as a student, right? So, I mean, right now, robotics is highly interdisciplinary field. So first, just make sure that you basically learn enough about AI, ML, but also learn enough about robotics, right? So make sure that you do some control courses, make sure you do some dynamics courses, you do mathematics courses, right? A lot of trouble oftentimes is that a lot of mechanical engineering students know quite a bit about dynamics and growth. They know very little about modern AI, ML. A lot of computer science students know quite a bit about AI, ML, but they know very little about advanced control methods, advanced modeling. So to make contribution, we need to make sure that we have well-rounded education, and then try to do problems which somebody cares about. The real problem somebody really cares.
As you said, there is a gap between like the technical people and the domain experts.
Right.
So when you said that also using like the precision surgery, so like how do
Minimally invasive surgery.
Right. So how do these kinds of innovations come to you? Because like doctors do not like trust like how does the idea even come into this class? Like even in agriculture, how should the idea determine that
So solutions I don't know, problems we all know about, right? You talk to customer, they can give you list of problems they're having, right? All farmers will come back and say, hey, they're wasting too much water, right? Every patient will tell you, why are you doing hardness or you are opening me up over here, right? Can't we really do something smaller, right? So I'm saying problems are well known. I don't think there's any issue for problems, right? Now, solution I don't know, right? Then the thing becomes, okay, fine, we are using too much water, we are using too much fertilizer, we are using too much pesticide. How to fix it is something that we need to start then having a team room to figure this out. But most societal problems, I don't think there's any disagreement, right? We know system pollution, we know, so problems, we have pretty good understanding of
are the major problems of the world, but there are many small things that can be solved, I think, through robotics, which people, technical people might not know, and the people in the domain might not know can be solved through.
Domain people can articulate the problem. I mean, they may not, I agree with you, they may not know the software, right? But whichever sector you focus on, you have to go work with the people who tell you and share with you what the problem is, right? And then you can say something can be solved today, something will be 5 years down the road, something will be 50 years down the road, and take the best guess, and then you start to